it's recording and it's saying it aloud. We are working on the bell ringer. Week 5, bell ringer 2. And this is a lot of stuff to read. Let's start reading. First one. It's saying the value of a newly purchased car was 25,000 initially. As soon as you purchase it, should I call that a 0 year or a 1 year? How many years are there on a car when you purchase it as a new car? There are no years on that. 0. At year 0 or in the beginning of the first year, that's how I can say it, the value was how much? 25,000? In the beginning of the first year or at year 0, the value was 25,000. Then the 1 year passed. How much is the value now? 21,250. What is the value at the end of the second year?
Oh, 18,000.
Very good, Anaya. That's a good one. 18,062.5. How did he get it?
This one?
This was?
Yeah.
How did he calculate it? What was your logic? Can you tell us?
I did the equation. I changed the numbers.
So tell me if you have used this formula, which was the decay. Is that right? That's a perfect thing to do. Because this is the depreciation and depreciation with the percentage. It's not a fixed amount every time. So what has been done here, look at this. What Anaya did, she took the 25,000 and then she used the formula for decay or depreciation and she applied this. 15 divided by 100. Oh, you know what? I do remember that if I'm writing the stuff over here, it will not be recorded in the video because it's on the screen. So what I will do, I will take you to the notes and we will write this stuff over here. This will definitely be recorded. I just recall that thing in time. So let's write it over here. What I was saying, initially, the way we have done it, or I should say that Anaya has done it. So I'm taking a little bit of time trying to fix it. Here, draw, here we are. Okay, listen. What we did, we are trying to give it a name. Years here. 0, 1, 2, and the value here in the beginning of the first year or at the 0 year, the value was 25,000 for the car, and then end of the first year, Anaya has calculated the value was 21,750. 250. And then at the second year, 18,062.5. Perfectly done. How did she calculate it? That's what we were trying to figure out. So what she did was a 25,000 times 1 minus 15 by 100. Why 15? Reason is here 15 because in this case we have here a 15% less every year. Every year the value is going down by 15%. So can I do this over here? Look at this. 15%, can I write it down instead of 1 minus all that stuff? If I will do this, and then finally, I will reach a number which is 0.85. 0.85. What does that mean? That means every year the value of the car is getting down by 85. Like every year it's 85% of the previous year's value. It depreciates to 15%, but what's the value every year that's left behind? 85% from the previous year. Got it? Is it being subtracted or added or multiplied? What's happening here? Huh? Subtract. If you're saying subtract, that means here we have a difference of 3,750. Is this the same difference over here also? If it's the subtraction, then I should have the same difference. So the difference is not same here. Difference is different. How much is the difference in this case? I will have to subtract from 21,250, 18,000, and so it should be something like 3,062.5. No, can you help me on this? 21,250 minus 18,062.5. Someone use the calculator, or you want me to use it? 3,000. Sorry? Thank you. 3,187.5. So this is another delta here now. Is it same from the previous year? Depreciation has changed. The next value will again be different. When the difference is not same, it's not a common difference. Remember, in the linear form, I will give you another example. I'm trying to bring in another table over here. Look at this. If we will try to plot x, 1, 2, 3, 4, and then y, a 10, a 14, an 18, and a 22. If we will try to plot this in Desmos, this will look like a straight line. If we will try to plot this in Desmos, this will not look like a straight line. Let's try it quickly. That will differentiate if it's linear or exponential. So where will I do that in Desmos? We can open Desmos here. In this one. So opening Desmos in okay, here. Graphic calculator, what am I doing? I'm trying to bring in here with a table. I'm trying to bring in here with a table the function with the values 1, 2, 3, 4. How many values are there? And my blue table, 4 values. And how many values are there? Another one, we will see that also. So here we have a 10, then a 14. Do you see the points there? 18 and a 22. So if these points are plotted in this case over here on the table, do we see it? Not yet. We see it now. Hold on. Let me, instead of this, I will make my life easier by changing the scale here. On this scale, for the x-axis, we have done this in the past also. For the x-axis, I will move it from 0 till 5 for 6, let's say. And then for the y-axis, I will move it from 10 up till 30. Okay, let's do it till 30. Thank you, Karen.
No, thank you.
Who was it?
Me.
Okay. We have a recording, we can just tell. Good. If you did that, very good. So this, does it look like linear or an exponential? Does it look like linear? Clearly linear. So this linear plot, now let's analyze the linear plot over here. If I will look at the linear plot and if I will come back over here and try to see if the differences are same or not, then the thing that I'm trying to share will be clear. Here, what is the gap? 4. And what is the gap for the next term? 4. What's the gap for the next term? We do have a common difference. Agree? Whenever you will have a common difference, it's linear. Whenever the difference is not common, like in this case, it's normally not linear. This is different. But we do have one thing here. If you have noticed, every single time what we were doing, we were multiplying it with the 0.85 to get the next value. Does it make sense? Every single time we are multiplying with something, so that multiple over here is my common ratio. Michaela, what we will call that? We will call this a common ratio. Why is it a common ratio? Because every single time I'm multiplying, Michaela, every single time I'm multiplying my initial value with 0.85 to get the next result. This is not a common difference. This is a common ratio. And whenever we are working with the common ratio, the curve will be exponential, not the linear. This is the exponential case. And when the common differences are same, whenever we have the same common difference, this type of a curve will always be a linear fit. Make sense? Now, this is the car that we are looking at in the first question of our bell ringer. Is it linear or exponential? Exponential. So one thing decided that over here, it's not linear, it's exponential. Now, what's the rate of change for the exponential? Is it decreased to a 15%, like in the last choice, or it's decreased to an 85% compared to the previous one? Huh? From 25,000, it dropped to 21,000. Then from 21,000, it dropped to 18,000. So every next value is the 85% of the previous one. Or 8.85 times. Where is it? And the second choice over here, we have the 0.85 times the value of the last year. That's what we did. For every year, what did we multiply it with? We multiplied it with a 0.85 here. So every single time, the value is getting multiplied by 0.85. So what's your choice?
B.
B. Now, if B your choice, tell me one thing. It's exponential. It's not the linear. Do we have a common difference case or common ratio case? Common ratio. So if I'm looking at the second question, it's asking you, justify your answer. For the justification, use these verbs. So what will you use? You will claim, we are working with the common ratio, not with the common difference. It's not a slope rate of change. It's actually the common ratio. And we will every single time multiply with the same number, which gives me an exponential function. There is a reason I went that fast. Why? Because I want you to use your own words to respond to this. While responding, make sure that you're using these words. Which words? Slope, common difference, common ratio, and intercept. It's not a case with the common difference because common difference means we are subtracting something. We are not subtracting, we are every single time multiplying with a 0.85. That's what should go to your. Now, second question. We have here a linear plot. You clearly agreed that this is linear. Visible also the green ones were real ones or the actual ones or the observed values, and the blue line is the predicted line, the prediction line. If I will ask you, what is the prediction when the x or the time is 20? What will you do then? The prediction for the time 20. How will you do it? You will check in the x-axis where the time is provided in the minutes, and in front of 20 you will see the blue line, and for the blue line you will try to figure out what is it correspond to. What does it correspond to? Where it's somewhere between 53 and 54. So that should be the temperature report. We can do the prediction like this. So linear curve, what are the choices? With every next minute passed, the temperature increased by 5 degrees. Is that right? No? Why? Because it's decreasing. Okay, second choice. With every 10 minutes passed, the temperature increases by almost 10 degrees. Is that right? No? So you're saying with that is not correct. Third option. With every 10 minutes passed, the temperature decreases by 10 degrees. Is this right then? Or no? What do you think about it? From here, from 0 to 2, from 2 to 4, 2 to 5, 5 to 6, all the way, how much did it decrease up till here compared to the initial value? That's what I'm looking at. Then the fourth option, with every, I missed a Y here, with every next minute passed, the temperature decreases by 5 degrees. So we can definitely remove those choices where it's saying increase. It's not increasing, it's decreasing. So the first option is not right, second option is not right. We need to choose between this third and fourth. Which one is correct? And you can look at the plot for that. Which one is correct? D. So you're saying when it changed from 0 to 10, from here up till this change from 0 to 10, the temperature decreased from 80 almost to 75. Is that right? Huh? Where did it fall? To somewhat. You can zoom in and look at the numbers also. If I will try to figure out what's the value almost here, that looks like a 70 to me. So with the 10 minutes passed, how much did it decrease? 10 degrees. Because from 80, it dropped to 70. So with 10 degrees, with 10 minutes passed, how much did it decrease? 10. So what's my right choice here in that case? C is the right choice. Explain in a few sentences your logic to conclude the previous result. Now, again, common difference. The slope of the line is negative. It's decreasing. So logically, when it's decreasing, going downwards, the slope is negative. That's what you will do. Negative is telling you it's decreasing. So we cancel the options of increase. And then we looked at the graph, and graph showed us that with the 10 minutes passed, it dropped to 10 degrees. So it dropped for 10 degrees, and that's what is the right choice. Use your own words. Use your own words.